This conference will now be recorded.
Good morning to all. So, before getting into today's topic, we just discuss about the previous week topic. Okay, what we have seen in the last class. Our last class topic is assembly language program development tools, modular programming, stack operation. Okay, so assembly language programming development tools are editor, linker, assembler, linker, locator, debugger, and emulator. Okay, these are all tools of assembly language programming using MASM. Right? Modular programming is nothing but it is a principle of divide and conquer. So we have a huge complexity of application or issues that will be divided into number of submodules and is given to individual teams. As I told you earlier, example present in corporate sectors. Okay, so the huge problem or project will be divided into number of sub projects and disseminated to the teams. Okay, different teams. Finally, all the teams achieve the result, and all the results are collectively given as single solution for a problem. Okay, that is said to be divide and conquer method modularity. Okay, so how modularity is playing here? So if we go for any real-time applications, the similar way we are going to troubleshoot and we are going to create a program for that particular application. Okay, that is modular programming. Next, stack operation. As we know, the concept behind stack, it is nothing but first in, last out. Okay, so we have two basic instruction used to put and retrieve the data out of stack, is push and pop instruction. And also we have stack pointer, which always points top of the stack, empty stack, right? And then in this session we are going to look at MASM 8086 interrupts, classification of interrupts, memory organization. Okay, so already we know MASM is like nothing but your Microsoft assembler. And what do you mean by the concept interrupts? Can anyone tell me what is interrupts? You're always interrupting a class. You're always interrupting the lecture delivery, like that. Yes, disturbances. So in 8086, very good Gayatri, it is like a disturbances but not exactly the disturbance. Okay, so what is interrupt is, it is very simple. Okay, if a faculty is taking a class, okay, a real-time class, not virtual class or something, if just before I had an interrupt, right, from Sajita. Correct. So a faculty taking class, in between some students of other department will come and get some names for some events. Okay, so that is what interrupting the class. Okay, so in 8086 or any processor or controller, interrupt concept is nothing but your processor. Okay, say MUP, MP or MUP processor na MP or MUP, micro is mu. Okay, so we are having n number of lines, the main program. Okay, I'm having n number of lines. Okay, and my processor will execute first line and execute the second line, likewise it goes on. Okay, in between, if I have a subroutine, here we have subroutine, that is interrupt. Interrupt subroutine is nothing but a program. Okay, a separate program. This is your interrupt program. Okay, so here in this third line, okay, when executing this third line by the microprocessor, I have interrupt over here. Okay, so what happens? My microprocessor stops working from second. Okay, it's going to start the third, but at the same time, I'm getting my interrupt signal. Okay, so the second data up to the second line, the data will be stored in the memory, and processor comes to my interrupt program. Okay, so it stops serving this main program, and the processor comes to this interrupt program. Okay, after executing this number of lines in interrupt program, it comes back to the main program. Okay, after this execution of your interrupt only, it will goes back to your main program. Okay, this is interrupt. Okay, so until then the data will be stored in the memory, right? After that it executes from where it left to the end of the program. This is a concept of interrupts. Okay, interrupts is nothing but it is a subroutine, a program. Okay, right. So next, classification of interrupts and memory organization of 8086. Okay, this is what we are going to look at in today's session using MASM. Okay, MASM, we know MASM is nothing but it is an Microsoft assembler. We have a .asm file, obj file, object files, then create a .exe files using link, correct? And once you have created this .exe file, we can debug the program. The steps to be followed for executing the application using MASM, right? Okay. First, we are going to edit the program. We're supposed to give a file name which with an extension .asm, and we have to link the files. And next, followed by linking, you have debugging, correct? And finally, you will going to execute your program. This is the steps to be followed for MASM operation. And next, interrupts. Interrupts we have basically in 8086 we can generate up to 256 interrupts. Okay, so 256 software interrupts can be generated, out of which these five interrupts are important. Okay, so interrupt 0, interrupt 1, 2, 3, 4 are very important than the other. Okay, all these interrupts are software generated. I can program, I can name my interrupt as interrupt 25, interrupt 39, likewise. Okay, so these five interrupts are important in interrupts of 8086. Okay, so software interrupt can be given as int NN. Okay, so it can be up to 256. Okay, 256 interrupts can be generated. And what is your int 0? Int 0 is reserved for divide by 0 error. Okay, so when you have divide by 0 error, divide error, if I have a calculation or computation done wrong by the division, okay, then that is comes under your interrupt 0. Okay, say for example anything divide by 0, you will have a division error. If your calculator will not calculate the value. If you go with that value, 5 divided by 5 will get 1. 5 divided by 0, it will gives me math error or calculation error in the calculator, correct? So that is divide by 0. We cannot omit this error. Okay, and next, block interrupt 1, single step operation. So individual instruction will be executed using this interrupt 1. One by one instruction will be executed using clock signals. And the next one is interrupt 2. So this is NMI. NMI interrupt, non-maskable interrupt. I have given you a pretty good example in the previous classes that we have mobile phones, we have calls and messages. Okay, so your calls will not mask at all. Your message can be masked. Okay, that should not affect the performance and operation of the calls. Okay, so your calls is non-maskable interrupt, messages are interrupt maskable interrupts, right? And next we have interrupt 3. It is reserved for setting a breakpoint. Okay, so what do you mean by breakpoint? If I have 50 lines of my program, okay, I'm going to set a breakpoint, 10 lines. I'm dividing the program into 10 lines so that I can troubleshoot my program easily. Okay, so if I troubleshoot the whole program at a stage, what happens? Then I couldn't able to clear or sort out the mistakes where I have done. Okay, so so the breakpoint helps us to clear the mistakes easily. Okay, it is user friendly, right? Next we have interrupt flow, that is to be overflow interrupt. Okay, so whenever you have overflow in the output result or memory location, then this particular interrupt will be generated. Okay, so next is what CLI STI. This is very important. We are going to set and reset our interrupt flag. Okay, where you can able to see the flag register. It is present in the architecture of 8086. Okay, flag register is used to showcase the status of the processor. Okay, whether it is doing any process or not. If it is doing any process, what happened? What happened to the results? Whether we have overflow or parity or zero or sign. Okay, these are all into consideration. Okay, it shows the status of the microprocessor. So I should clear this flag register, or I should set and reset it, right? So by setting, your flag is nothing but I'm giving 1 to my flag. Resetting flag is giving 0 to the flag register, right? Enabling the flag, disabling the flag. And next comes interrupt of 8086. Okay, done. So this is identifying interrupt sources. Okay, so how can you able to identify the interrupts? So we have three basic methods. One is software polling, hardware identification, right? So under software polling, we have to check each and every device whether we have any software interrupts in the program or not. We have written any software interrupts in the program or not. We should check each and every time. That is software polling. Okay, hardware polling is nothing but a daisy chain method. Okay, so for example, what happens when polling is done? Everyone are standing in a queue and waiting for their time to cast their vote, right? So similar way, each and every peripheral devices are waiting in a line, waiting in a queue, so that it will be performed with their interrupts by the microprocessor or microcontroller. This is hardware polling. Okay, which interrupts has highest priority, that will be executed first. That will be served by the microprocessor first. Okay, and next hardware identification now vector interrupt. Interrupt will be stored in memory location, that is vector interrupt. Okay, basically interrupts are classified into three types. One is maskable, non-maskable, vector, non-vector, hardware and software. Okay, so interrupt generated using hardware. Say for example, if you have reset button in the system, that is to be your hardware reset. Okay, hardware interrupt. And if you have created a subroutine, that is a program for separate program for your interrupt in the program itself, then that is said to be software interrupt. And next is what maskable, non-maskable. I have already explained you, right? Mobile phone calls and messages. Okay. The third one is what vector and non-vector. So under vector, your interrupt will be stored in memory locations. Okay, there is some predefined memory locations which serves only interrupt operation. We cannot able to put the program for any other peripheral devices in the particular memory location. That is said to be vector interrupt. I am dedicatedly assigned some memory location to the interrupts. Okay, interrupt programs. That is vector interrupt. Okay, non-vector interrupt. I can put any location for my interrupt program. That is said to be non-vector interrupt, right? And next is what daisy chained. So daisy chained, from the figure you can understand we have interrupt IR0 to IR6. Okay, so this interrupt will be connected to the OR gate. Okay, so what is the application of OR gate? OR gate is adding, correct? So here whenever you have interrupt in the lines with the priority, that will be added with the OR gate, and that is given as input to my interrupt present in the 8086. Okay, you can take this as 8086. 88 is also a processor, co-processor. We can take this as 8086 instead. Okay, this is 86. This is daisy chained interrupt. Okay. Next, interrupt masking. So interrupt masking is something that I have already given you, right? It includes certain types of interrupts by use of a special interrupt mask bit. Okay, there is a mask bit present in the register. Okay, we can mask the interrupts or we cannot mask the interrupts. Okay, and we can also set and reset your registers. Okay, non-maskable interrupt cannot be masked. So calls cannot be masked, messages can be masked. Okay, this is interrupt masking. And next, software interrupts. Software interrupts, it is of 256. We can generate 256 interrupts in 8086 using the software programs. And exceptions. What are all exceptions? Divide by 0, memory protection fault. Okay, this cannot be avoided. So these are all comes under exceptions of interrupts. Okay, and memory. So classifications of memory. So memories are used to store programs and data, right? So we have basic classifications, three basic classifications. One is processor memory, next primary memory, and main memory and secondary memory. Okay. So generally memories are used to store code and data. Correct. So in under your processor memory, what are all present in the processor memory? We have general purpose registers, segment registers, temporary registers. Okay, all these all comes under your processor memory. Okay, the space where the architecture gives me to store the information for computation is said to be your processor memory. And primary and main memory is nothing but I have room and RAM. Okay, and what is secondary memory? Secondary memory is an external memory device. Say for example, pen drive or USB pen drive or hard disk, floppy disk. These are all comes under your secondary memory device. Okay. And memory organization in 8086. Okay, so here we have banks. Okay, so bank 0 and bank 1, odd bank and even bank. We have 1 MB of memory that is coming from your address lines. Okay, 2 to the power 20 is equal to 1 MB. 1 MB of memory is there. Okay, so that is divided into two banks. One is odd bank and one is even bank. So your even bank is activated by the control of A naught and odd bank is activated by the control of BHE bar. Okay, so this is your memory. Okay, odd memory addressed and even addressed memory bank. Okay, so what is this memory? So this is your address. Whatever the memory, whatever the data we are going to put inside the memory, we are supposed to have two important informations. One is for address. Okay, where we are going to view according to the is address lines. Okay, so this is your address. It is common in both memories. Okay, A0 to A19. And what else is common? Data lines. Okay. So in odd bank we have higher data lines and even bank we have lower data lines. Okay. Look at this diagram. This is even. This is odd. Okay. You will have higher data lines in the odd and lower data lines in the even bank. Okay. So what is CS? CS is nothing but chip select signal which is active low. So when you have signals bar over the signal, then this is represented. This represented. You see that signal is active low. Okay, I am giving 0 here so that it will get active. If you give 1, it will not get active. Okay, 1 kurta, it will not get active. So you have to give 0 to this particular chip select signal. Okay, so it is mandated. That how we give supply and ground to individual ICs like that. It is mandated to give chip select signal to make your IC get into active state. Okay, and next here we have odd bank. Odd bank which is controlled by your BHE bar, and even bank is controlled by A naught. Okay, say if this is odd O irukka, so your controlling function will not have O, but here in the even your control function has O opposite to each other. Okay, so when you take even bank you should not go for BHE bar as your active signal, so instead I should go for A naught. Okay, this is easy to remember. Even bank E is here no E is here, right? So this is your odd bank or opposite. O should not be present as the active signal. So this is PHE bar, right? So this is what your memory organization of 8086. Okay. And next comes the operation, different operation depending upon the input of BHE bar and A naught. we have different operations. Okay, here we have seen how the memory ICs are interfaced. Okay, what are the parameters should be interconnected to the memory? That is, data and address is mandatory and chip select signal. Correct. And next, followed by that, we have memory organization operations. Okay, if I give 1 to BHE bar, what happens? Read and write byte at an even address. I can read and write at the even address, BHE bar. Okay, this is active low, this is active high. Okay, if it is 1, this one will be active. Even will be active. If it is 0, if this BHE bar is 0, then this odd is active. That is the order active. So when we have 0 at both the control signals, then we have switches the even address. Okay, and next we have 0 and 1 and the odd address. Likewise, different operations can be performed with the help of PHE bar and A0. And available memory space is EPROM plus RAM. Okay, and EPROM is nothing but electrically programmable read-only memory plus random access memory. This can be used to put and retrieve the data whenever we want. But in the ROM, we cannot able to change any program. Okay, during manufacturing time, during development of this processor time, they put a program, separate program for individual operations in EPROM, where users cannot overwrite or scribble over it. Next, interfacing SRAM and EPROM. Okay, so the difference between RAM and EPROM. Okay, look at the diagram. You could easily understand the signals present in the memories. Okay, so first of all, we have here N. This is N, this is M. N address lines and M data buses. Okay, address bus and data bus. Your data will be bidirectional and your address will be unidirectional. This is your static RAM, and this is EPROM. Okay, EPROM, and this is RAM, random access memory, read only memory. So here we have ground and VCC. Similar to that, here we have ground and VCC. This is mandate to get power to my IC. Okay, so address bus here. Similar way here we have address bus. Data lines here bidirectional. Here also data bus. Okay, and what happens next? We have to give chip select signal. That is given here as chip select signal. Okay, right. This is your chip select signal. It is also available in your ROM. Chip select or command enable. Okay, next we have two important signals, that is read and write operation. I can read and write data whenever I want in the RAM. So we have two functions over here, read and write. But in case of ROM, that should not be possible because here we have a read signal alone. We should not write the EPROM, right? So that provision is not available in the EPROM. So read is available in the EPROM. Okay, so this is very easy to understand. No need to mug up the things present in RAM and ROM ICs. Okay, so from the address lines, we have 20 address lines in 8086, so that the memory capacity will be calculated as 2 to the power 20. So this many values will be generated. Okay, 1024K is equal to 1 MB. So we have 1 MB of memory space starting from 00000 to all Fs. Okay, this is the range of memory capacity of 8086. Is this clear? Interfacing SRAM and EPROM. Static RAM and EPROM. So EPROM la we don't have any write provision, but in RAM we have read and write provisions. Okay. Other than your address, data lines, address lines, control signals like chip select signals, VCC and ground, we have read write signal in static RAM and read signal in ROM. Not write signal. Okay, so this 1 MB memory is split into two, 512 KB odd and 512 KB even. Okay, so 512 KB odd and 512 KB even space. And next comes interfacing SRAM and EPROM. Okay, so we can interface are 8086 along with the memories, IC, and also peripheral devices like 8259, 8257, 8255, 8251, 8254, etc. Okay, so out of which 8279 is programmable keyboard and display controller, 8257 is DMA controller, 8259 is programmable interrupt controller, and 8253 is programmable peripheral interface. That is also called PPI. And here you can see interfacing input, output, and peripheral devices. Okay, we have microprocessor, and the other hand we have input and output devices. How we are going to interface this? Interfacing is nothing but connecting between the devices. A connection is created between two devices to get an application. Okay, so we are going to have ports, buffer, ICs, interfacing circuitry as. Okay, so this is your interfacing of input output peripheral devices along with my microprocessor. So data transfer types. How we are going to transfer the data between these blocks? We have three basic classifications. One is programmed input output, interrupt driven input output, direct memory access. Okay. So under programmed input output, your data transfer is accomplished through an input output port controlled by software. Okay. So this is done by software programming. Okay. Next, interrupt driven input output is nothing but it is initiated by the interrupt activity, interrupting your main program and transferring the data between the blocks. And next, direct memory access. Without interfacing your processor into action and transferring the data between the blocks, input, output, and to the memory, and from input out, from memory to input output devices. Okay. So this can be done without interruption of microprocessor. That is direct memory access. That obviously reduces the time, and the execution of the output will easier and effective one. And program input can be classified into two. One is memory mapped and the one is input output mapped. That is all, and we are going to look at a few questions. Okay, so question and answer session. The size of memory in 8086 microprocessor is dash. Can anyone answer? The size of memory in 8086 microprocessor is dash. Can you able to follow today's topic? Do you have any doubt? Do you have any doubts? Doubts இருக்கமா? No ma'am, right. So then can anyone answer the size of memory in 8086 microprocessor? The size of memory is 1 MB. Okay. Define interrupt. Interrupt is nothing but it is in subroutine. Okay, which interferes your main program to get executed. Okay. What are all the types of interrupts? We have subroutine. Super Gayatri. Good answer. What happened to rest of the students? Always these students are answering regularly. Types of interrupts. We have divide by 0. Basic types are 3. Maskable, non-maskable, software, hardware, and vector, non-vector. Okay. Super. Very good, Nitya Shri, Vaishaka, Visvesha. Yes, very good. We have interrupt 0, 1, 2, 3, 4. Okay. So that is divide by 0, non-maskable, single step, non-maskable, breakpoint, overflow. Okay. These are all basic types of interrupts, out of which we can generate 256. software interrupts in 8086. What is SRAM? Static RAM. DRAM? Dynamic RAM. Okay, so this is end of this session. Static. Super Nitya. And now we're going to look at the next topic. Okay, we go on to the next topic as we have a few more minutes. Okay. Okay, the last topic of Unit 1. So far we have discussed MASM, 8086 interrupts, classification of interrupts and memory organization. Am I fast? Am I fast? Or is this okay? No, right. Okay, Vishwa, Gayatri. Okay, so this is last topic of Unit 1. That is instruction set. Okay, in the previous session we have studied. Okay, Subhashini, thank you. We have studied about MASM, interrupts, classification of interrupts, and memory organization. Okay, so next we are going to look at instruction set of 8086. Okay, so already we have seen addressing modes of 8086. Okay, similarly we have instruction set of 8086. So number one is data transfer instruction, arithmetic logical instruction, shift rotate instruction, program control transfer instructions, iteration control instruction, machine control instructions, flag manipulations instructions, string instruction. Okay, these are all instruction set. So what is instruction? The instructions are defined by the manufacturers, okay, during development of the particular processor or controller. Without that instruction, your processor or controller will not get into action. That will not understand what is going to do, what action should I get into அப்படின்னா your processor and controller will not know. Okay, so this is instruction. If I want to add data, so I'm going for arithmetic instruction. If I want to move data, I should go for data transfer instruction. If I want to check some conditions, I should go for iteration control instruction. Okay, so likewise. Okay, if I want to execute any string operation, hello or CCE like that, if I want to execute or if I want to display the strings, then I should go for string instruction. Okay, so here data transfer instruction. What is the application of data transfer instruction? So we can able to transfer data between different blocks. Say different blocks are your memory, internal registers, or input output ports. Okay, so anything can be your blocks. I can transfer data from memory to internal register, or from internal register to memory, or from one register to another register, or from input port to internal register, or from internal register to output port. Likewise, I can transfer the data, move the data. So once you move the data from one block to another, the present data will not erase. Okay, the copy of data only moving from one register to another register. Okay, and next move instruction. This is move instruction. Already we are going through with instructions, right, programs, right? So this will be definitely easy for you to follow. So move destination comma source. Okay, so your data from source will be moved from this place to this place, always from right to left. This is your syntax, move destination comma source. It is used to transfer the word or byte from one register to another register or any other blocks. Okay, that is defined here as destination and source. From source to destination, it will be moving the data. And this is a few examples. Okay, so move bx comma 00f2, move cl comma 2000 inside the bracket. So whatever the number given inside the bracket, that should be considered as address. And next move inside bracket 589h comma bx content will be moved to 589h. Next move ds comma cs. Okay, this data present in the cx will move towards ds. Okay, likewise examples are given. Next we have push instruction. Push instruction, push cx, push dx. Okay, so by default your stack pointer is decremented or incremented by 2 because it is 16-bit processor. We have a memory location which is capable of storing only 8-bit. Okay, so if you want to store 16-bit, I should go for decrement by 2 or increment by 2 in the stack. Next, pop instruction. Pop instruction is similar way. We are going to get the data. It automatically incremented by 2. Push instruction automatically decremented. Pop automatically incremented by 2. Next, in and out instructions. So in and out instructions are used to connect your peripheral devices using input-output port. So these are all some examples of in and out. In either comma 0F8H. Move DH, 30F8H. Okay, so the content present in this side 0F8H will be moved to accumulator. Okay, so DX register data will be moved towards accumulator. This is your input operation. This is output operation, right? Exchange operation. Exchange general format is EXAHE, destination comma source. Okay, this exchanges the content between the source and the destination. So few examples for exchange: Px, Cx, Al, Cl, Ax, sum of Bx. Okay. Next, arithmetic and logical instructions. So add, subtraction, multiplication, division, compare, add with carry, subtraction with borrow. Logical operations can be and or not XOR. Okay, for AND operation, we have example add a comma a destination comma source. This is a general format, and x comma bx, ax comma bracket si. These are all few examples under different addressing modes. Okay, immediate addressing mode, register addressing mode, register indirect addressing mode, direct addressing mode, and immediate addressing mode. Okay, so next add with carry. Okay, so addition operation, same operation now, but here we are going to add the carry flag bit. Okay, this is add with carry. Next, subtraction. Subtraction, destination, comma, source. Already we all know, right? Sub x, comma, bx. Okay. Different addressing modes, we are giving example. Subtract with borrow. SBB is subtract with borrow. Next, compare instruction, CMP. Okay. Compare instruction compares both source and destination. Compare ax, comma, 0100. Compare bx, comma, cx. Register between register, we are going to do comparing operation CMP. Likewise. And increment, decrement instruction. Increment AL, AL plus 1. Decrement AL, AL minus 1. Okay. So this is your increment operation and decrement operation. Next, add on instruction and logical operations and AL, BL and CX, AX. These are a few examples. Logical and operation will be performed using this instruction. Similar way, or instruction or destination, source. Not only one data will be complemented, so not AX, right? So next is XR, AX, PX. Okay, XR operation. So operation gives high output when two inputs are dissimilar. Okay, similar இருந்துச்சுன்னா it will give 0. Dissimilar இருந்துச்சுன்னா output will be high in XR output. Shift and rotate. So shifting is moving, correct? So I'm shifting this register to that register. அப்படின்னா it is again similar to your moving instruction, transfer instruction, the shifting. But in this shift and rotate, you have, let me check. So this is shift arithmetic left. Okay, shift arithmetic left and logical left. Okay, in this execution, you can see here example: move BL comma B7H SAL BL comma 1. So this BL is made B7H. So I'm going to transfer move B7H into BL. Next, your shifting operation, shift arithmetic left BL comma 1. It should shift the data left side by one time. Here the number of count will be given. If it is 2, left shift by 2. If it is 5, shift the value by 5. 5 times shifting takes place, right? So before execution, your B7 will be like this. Okay, so B7 will be expanded in 8421 code. One second. So under 8421 code, I'm going to expand my B7 as this, like this. Okay, so here you can see this B7, this B7 will be written here, correct? This is your 7 value, this is your B value. What is B? 0 to 9, A to F, 10, 11, correct? 8, 9, 10, 11. Okay, this is B equivalent and this is 7 equivalent. I'm going to shift your value left by 1. This is shift arithmetic left. Every times 1 time. So left by 1. This is your carry. By default, carry bit is equal to 0. After execution, after shifting 1 bit left, what happens? This 1 comes to carry. This 0 comes to B7. Okay, this 1 comes to B6, this 1 comes to B5, this 1 0 comes to B4, this 1 to B3, and this 1 to B2, and this 1 to B1. What happened this B0 value? So there is no value, so I am obviously make it as 0. Is this clear? This is how you are going to shift your data. Shift by left or shift by right. Okay, this is SHR, shifting instruction right side. அதுக்கான example அதிலிருந்து பார்த்துக்கலாம், right? So ROL rotate operation. The general format is ROL destination comma count. This is not source, this is count value. General format will be having destination comma source, right? Here it will have count value, right? And next, this is your rotate operation. So what happens when we rotate B7? Take that example, B7 here. Okay, I'm going to rotate BL, comma 1. 1 times I'm rotating. So basically, this is your B7. Correct. This is your B7. So the carry bit is equal to 0 by default. And next, followed by that, I'm doing my rotation operation. After execution, 1 time rotation, what happens? Here we have 0 by default. This B7 moves to CY carry. Likewise, all the data will be moved left side by 1. And finally, we'll have no value in B0 while we shifting the data. Correct. But here, in case of rotation, this data will be comes to the LSB. This is rotation. Okay, rotation என்னடா சுத்திட்டே இருக்கிறது rotation. Correct. It keeps on rotating. Whenever I go for rotating operation, it will rotate the data like this. Correct. So this one from the carry will be moved towards my LSB B0. So here we have 1 instead of 0. When you have 0, when you shift your data left by 1, you will have 0 in B0. When you rotate the data, then you will have 1 in the B0. That is rotate right side rotation. And program control transfer instruction. There are 2 instruction classifications. One is conditional, another one is unconditional. Okay. So under conditional, we have J condition. Unconditional transfer, we have call, return, and jump. Call instruction is used to transfer execution to a subprogram or procedure. Okay, I'm calling a function. So this is the instruction which I am going to get an external function call, right? So once you call the function, then you should return the program. So this is the instruction which your processor can return to the main program from the calling function, right? Next, jump instruction, unconditional jumps. We have short jumps and fast jumps. Okay, depending upon the condition available in the program, I can go with short jumps or short jumps. Okay. So conditional jump na J, true or false, whether the condition is satisfied is true or not. Okay, this is conditional jump. Iteration control instruction. So next is loop instructions. Okay, so why we are going for loop? So continuous iteration. It is again like a condition now. So yeah, loop if is equal to 0, loop is not equal to 0. Okay, the loop repeats depending upon the iteration condition. Your loop repeats. It executes a series of instructions some number of times. Okay, so number of times it will execute the a series of instructions. Okay, it automatically decremented in course of iterations. So if we have a condition like 5, so first iteration and it will decrement the value 5 to 4. Second iteration it will decrement the value 4 to 3. Likewise it reaches 0. Okay, once it reaches 0 it comes out of the loop and execute the next instruction. If not, and that loop will execute it forever. Next, machine control instruction, we have halt, wait, escape, lock, and NOP. Okay, so machine is nothing but your processor. So I can halt the program, make my processor to wait or escape. Okay, or no operations can be done by your processor. Anything can be done with the help of machine control instruction. And next we have flag manipulation instructions. Okay, so flag manipulation means I can set and reset my flag registers. Okay, set st set cl clear. Okay, that is set carry flag, clear carry flag, cmc std direction flag. Okay, complement carry flag, clear data flag, set data flag, clear interrupt, set interrupt. Okay, all these are manipulations of flag register. And next we have a string instruction. String instruction, it will end with yes. Move yes. Okay. So before instructions you will not have yes because that is deals with the numbers. Here we have yes at the end of the move instruction, data transfer instruction, which represents string operation. Okay, move yes b, string byte, string word, repeat equal to, repeat not equal to, repeat not equal to 0. Okay, LODS, load data segment, load load data segment string operation, load data segment string byte operation, STOS is store, LOD is load. Okay, CMP is compare, compare string byte, compare string word. Okay, all these all deals with string operation. That is why at the end of the instruction we have yes, SB, SW, right? Finally, we reached our questionnaire session. What is instructions? It is a instruction is nothing but it is created by the manufacturer to execute application, okay, by the processor. What do we do with the instruction? In order to execute any application, we go for instruction set. Okay, so name the classification of instructions set of its arithmetic instruction, logical instruction, program transfer, iteration control, stick instruction. Okay, flag manipulation instruction, processor control instruction. Okay, these are all some instruction types. What is loop? Define loop. Loop is a continuous iteration. Till the condition gets satisfied, the iteration continues. Okay, once it satisfies the condition, it comes out of the loop, right? And define the term near and far. Near and far is nothing but it is like a memory location which is nearer to your process. Is said to be near. That is main program memory location. If you have a near value to jump, then that is to be near. If it is out of your memory location, I mean memory range, then that is to be far. So this is of unit 1 over. Okay. If you have any doubt, let me know or we'll wind up the class. From next class, we are going to look at unit 2. No doubt. Right. Thank you, Ma. Thank you. Class dispersed.